Okay, just some basics of circuit electricity here. Voltage is obviously a key concept. Voltage is also known as electromotive force, or also sometimes as potential. Now, to understand how voltage affects a circuit, it's helpful to have a microscopic model of a voltage source, say like a Duracell. What makes the negative end negative is excess electrons. What makes the positive end positive isn't excess positives, it's a lack of negatives. So electrons are lost here, and there's electrons in surplus here. Now, it's chemical reactions that happen at the positive and negative terminal that actually do this, and you can see that there is energy that's going to be associated with having excess electrons here and having a lack of electrons here. And it's that energy that we refer to when we define voltage as the ratio of energy to charge. So this is the electrical potential energy, and that'll be in units of joules. Of course, Q is a charge in coulombs, so a joule per coulomb is a volt. Now, that's still somewhat abstract. It's helpful to have an analogy. A cell separates charge and creates potential energy, just like on a ski hill, a chairlift lifts skiers up to the top of the mountain. It separates them from the earth. So the positives and negatives in a circuit are separated from each other, just like a skier is separated from the earth by a chairlift. So the voltage gain in a cell is kind of like the height gain on a chairlift. And of course, a current will flow out of the positive terminal around through the circuit, through the load, and then back into the negative terminal. And so that current flows through the resistor, and there's a voltage drop in the resistor. Well, that's like the height loss that the skier experiences when you go down the run. Going downhill. So a resistor is like a ski slope, and a cell is like a chairlift. Now, Ohm's law, oops, what just happened there? There we are. Ohm's law relates the amount of current flow to the voltage drop and also to the amount of resistance. The amount of current flow that you get varies inversely with the resistance and directly with the voltage, but we don't usually write it like that. Usually we rearrange it and say V is I times R. V is the voltage drop across the resistor in volts. I is the current flow through the resistor, that's in amps, and R is the resistance, and that's in ohms. 1 ohm, you could see, is going to be a volt per amp. Now, we said that voltage is the energy per charge. So that means the energy can be found for a given charge if you know its voltage. Now, as current flows through resistors, the voltage is lost and transformed into, say, heat and or work, and power is the rate at which that energy is transformed. So an energy is a charge times a voltage, and we divide by time, that's a power. Then we can group that, that's going to be voltage times Q over T. Now voltage is the energy drop per charge in joules per coulomb. This is the coulombs per second of charge flow, and that is the current. Because a coulomb per second is an amp of current. Q is in coulombs and time is in seconds. So what we find then is that electrical power is the product of voltage and current. And the units are watts, and a watt, of course, is a joule per second. And you can see that this equation is dimensionally correct, because if you multiply joules per coulomb by coulomb per second, the coulombs cancel, and indeed you get watts. Now, if you need to solve for energy, you just multiply the electrical power by time. That would, of course, be in joules, but a joule is a fairly small amount of electrical energy, so it's conventional to use something known as kilowatt hour. Kilowatts 1,000 watts, an hour is 3,600 seconds. Multiplying those together, you get 3.6 million watts times seconds. But watts times seconds is, of course, joules. So a kilowatt hour is 3.6 million joules. It's a much larger unit of energy. Your home probably uses 1,000 or 2,000 kilowatt hours each month. The efficiency is just defined as the benefit or the output over the cost, which is the input. And that can be a ratio of power output to power input, or sometimes it's a ratio of energy output to energy input, and it's always less than 100%. So those are some basic circuit concepts, really definitions. And then in terms of the concepts of circuit analysis, there's two, Kirchhoff's laws. First of all, KCL, the current law, basically says the charge doesn't appear or disappear. So for instance, if you've got a junction between two wires, then the amount of flow that's leaving the junction is the same as the amount that's flowing in. So at a junction, the sum of the currents in must equal the sum of the currents out. That's Kirchhoff's current law. The second principle is the voltage law, and that says that energy is conserved. So as charges flow around a circuit, they're going to gain energy in the cell, and then they're going to lose energy in the resistors. The electrical energy is going to get transformed into heat, thermal energy, and or light, and or work if it happens to be a motor. So what the voltage law says is that if you go all the way around the circuit, the sum of the voltage, and that's going to be the gains, which are going to be positive, minus the losses, which are going to be negative, have to be 0. This is for a complete loop. So for any complete loop in the circuit, going all the way around, the gains have to equal the losses. So the gain in the cell would equal this loss plus this loss, because that completes one loop. Alternatively, the gain in the cell equals this drop plus this drop, because again, that constitutes a complete loop. So we've got Kirchhoff's voltage law, which is applied to loops, and then we've got Kirchhoff's current law, which is applied to junctions. A couple of examples. So here, simple circuit, we notice that there's no junctions, and with no junctions, that means that the current flow will be everywhere the same, because there's nowhere else for the charges to go. So if there's 2 coulombs per second flowing this way, there must be 2 coulombs per second, or 2 amperes, everywhere else in this circuit flowing in the same direction. So that's the current flow. Now for the voltage law, as we go around the loop, the gains have to equal the losses. So there's a gain of 120 here. We see there's a 40 volt drop across this resistor, so there must be an 80 volt drop across this one. And then the gains and the losses will be balanced in this loop. Our next example, if we consider first the current, we see there's 5 amps of flow coming from the positive terminal of this cell. There's a junction. We see that 1 amp is going to flow down here through this resistor. The remainder, which is 4 amps, must flow through this wire, because Kirchhoff's current law says that currents in equal currents out. 5 amps in means you've got to have 1 plus 4 going out. Here's another junction, and this 4 amps is again going to divide. It seems at first that both of them are unknown, but if we look over here, we see there's 2 amps of flow at that point. Working backwards, there had to be 2 amps of flow there. Then by currents in equals currents out, there must have been 2 amps flowing down this way. So this is still the 2 amps, like that. it's going to recombine with the 2 amps flowing in that wire. So you'll have 4 amps flowing to the left. There was 1 amp flowing down here. The 1 amp will combine with the 4 and give you 5 amps of flow out here. So that completes the analysis of the currents by Kirchhoff's current law. Remember, the current law says that at a junction where wires join, sum of the currents in equals sum of the currents out. Next, we apply the voltage law. The voltage law is a loop law, and it says that in any loop, the gains have to equal the losses. So in this loop here, you gain 60, you must lose 60. That means there must be a drop of 60 across this resistor. Here's another loop. Gains must equal losses. If you gain 60 in the cell, you must lose 60 in this resistor. Here's a final loop, this one around the outer resistor. There's a gain of 60. There must be a loss of 60 across this resistor. A third and final example here, 60-volt cell. Let's do the loop law first. You gain 60, you lose 10. There's a 10-volt drop there. If we consider this loop, the voltage law says that the sum of the volts is 0. And that's the gains minus the losses. So there's a 60-volt gain, a 10-volt drop. There must be a 50-volt drop across this one for that loop to balance. Then for this outer loop to balance, there's a 60-volt gain, a 10-volt drop. This one must also be 50 volts. So if we rearrange the circuit a little bit so that the resistors point downhill, we can think of it again sort of like a ski hill. It's a 60-volt high mountain. There's a 10-volt drop. At that point, there's a junction. That's this junction right here. And skiers have to choose. They can either drop 50 to the ground this way and complete that loop, or they can drop 50 to the ground this way and complete that loop. Either way, the sum of the volts, the gains minus the losses, must be 0. That's the loop law. Current we can fill in fairly quickly, 5.5 amps there. Half an amp going down means that 5 amps must be going around the end here. That 5 amps is going to recombine with the half amp flowing down this way. Half plus 5 gives again 5.5 amps flowing back through the cell. A final concept from elementary circuit analysis is the idea of an equivalent resistance. Now we're going to use the S and P word. Okay, the S word is a series circuit. Series circuit has resistors connected in a row with no junctions in between. So these three are in series. This one here is not in series because of this junction, so these resistors are not connected in a row. So this is not simple series. Now, for a series circuit, the voltage law would say that the gain in the cell minus those 3 drops has to be 0. So let's say the voltage in the cell is Vt, and let's call the 3 resistor drops V1, V2, V3. So we see that the total voltage provided by the cell equals the sum of the 3 drops. Now the current law says that at a junction, currents in equal currents out, but there's no junction. So the current is going to be everywhere the same in that circuit. So you'll have the same current flowing through this resistor, the second one, and the third one. Now you can show using these 2 results that the total resistance of a series circuit is just the sum of the resistors. So in the series, the total resistance is the sum of Ri, where I is just an index that you sum over the number of resistors in the series. Then here's a simple example. We have 100 volts in the cell, 3 resistors. They are connected in a row with no junctions in between. So the total resistance will just be their sum. So it's 15, 5, and 5. It's 25 ohms. The total current flow from the cell will then be 100 volts over 25 ohms is 4 amps of flow. Now, by Kirchhoff's law, there's no junction, so there must be 4 amps of flow through this resistor, 4 amps of flow here, and 4 amps of flow finally through this resistor here. We can then, for each resistor, multiply the current by its resistance according to Ohm's law to get the voltage drop. So 4 times 15, there's a 60 volt drop here. 4 times 5 ohms, 20 volt drop there. 4 times 5 ohms, 20 volt drop there. So we notice that for the loop, and there's only one loop here, that the gains in the cell, which is 100, minus the drops across the three resistors, 60, 20, 20, do sum to 0. So this is consistent with Kirchhoff's voltage law. So we have a good solution. Now the other word is the P word. The S word is series. The P word is parallel. A parallel circuit is one where the resistors are connected at the top and connected at the bottom with nothing else in between. So those three are in parallel. These two are not in parallel. And the reason is this resistor up here. So these two resistors are directly connected at the bottom, but they're not directly connected at the top. This resistor lies in the way. So these are in simple parallel, these two are not. Now what the voltage law would say about this circuit is for any loop gains equal losses. Okay, well here's one loop. So the cell voltage gain would have to equal the voltage drop in this resistor. If you consider this second loop here, then the voltage gain in the cell will equal the voltage drop across this resistor. And the same thing for the one on the end. So those voltage drops are all the same and they equal the voltage gain in the cell. Now for current, the total current from the cell is going to split at this point. There'll be a current I1 that goes down in that direction. If we call this I2 and this I3, and if we follow it down to this junction, we'll see that I2 and I3 add together to give you the total current in this wire, and then I1 adds in as well, so that the total current going back through the cell is the sum of I1 plus I2 plus I3. And you can prove that the total resistance, the reciprocal total resistance, is the sum of, I should say plus dot 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 there. Let's do that. Erase. Don't make a mess. Okay, plus dot dot dot. So this is the sum of the reciprocal of the RIs. One final example or two here. Okay, we did that one already. Here's our example. So we just want to solve this circuit. So you can see there's 60 volt gains in the cell. So for this loop, there must be a 60 volt drop. For this loop, there's a 60 volt gain, so there must be a 60 volt drop. And for this loop on the end, there must also be a 60 volt drop. You see, skiers have to choose, right? They have to go down this way to the bottom, or this way to the bottom, or this way to the bottom. And either way, they're going from the top to the bottom. Now we can find the current, because of course if V is IR, I is V over R. So there's 6 amps of flow here. 60 over 15 is 4 amps of flow. 60 over 20 is 3 amps of flow. So there'll be 7 amps when the 4 combines with the 3, and there'll be 13 amps of total current when the 7 and 6 combine. Now, given that the total voltage is 60 and the total current is 13, we can, or rather one other way to arrive at that total current of 13 amps is to consider what the total resistance would be. Now in parallel, the rule for adding resistors is you add the reciprocals and then take the reciprocal of that. So 1 over RT is going to be 1 over R1 plus 1 over R2 plus 1 over R3, or as it's sometimes written, do the sum of the reciprocals and then take the reciprocal of that. So this is going to be a 10th plus a 15th plus a 20th, and then take the reciprocal of that. The common denominator is 60. That's 6 on 60, 4 on 60 and 3 on 60. 6 and 4 and 3 is 13 on 60, and then you take the reciprocal. So if that's the total resistance, then the total current would be the total voltage over the total resistance. The total voltage of the cell was 60 volts, and if you divide that by 60 over 13 ohms, multiplied by the reciprocal, you get 13 amps, which is consistent with what we had earlier. So that's a review of some basic circuit concepts.